All right. So we need to talk a little bit about the alkenes. And as we do that, we're going to have two primary problems. One, regiochemistry. Which of the two alkene carbons ends up with a given substituent? When we want to talk about this, we're typically going to use a distorted unsymmetrical example. This is a very common one, 2-methyl, 1-propene. The idea here is that there's a tertiary carbon, there's a primary carbon. So we get a really good idea of the effects of each. Second problem, stereochemistry. Now, before you start rolling your eyes, crying, or otherwise giving up on life, this is not the stereochemistry that we talked about in previous chapters. This is not R and S assignments. This is not enantio or diastereo. This is relative stereochemistry. Breaking an alkene is going to involve adding something to each of the two carbons. Relative stereochemistry is, do those add to the same side, what we call a syn addition of the former alkene, or are they added to opposite sides, what we call an anti-addition? There is a third option, which is we have no control, so we get a mixture of both, statistical mixture in most cases. However, since we're not creating enantiomers here, because we can't, starting from a planar starting material without any three-dimensional definition elsewhere, then the best we'll be able to do since we're starting from a planar starting material, we wouldn't actually be able to tell, because if we started from a linear alkene, even including the one up above, there's free rotation between those two carbons once the pi bond is broken. So that doesn't really help us. So when we want to talk about stereochemistry, what we'll frequently do is look at a cyclic alkene. The reason I'm pointing this out is because I tend to use the same examples for several different things, and it's not that there's anything magical about them. One case gives us clear regiochemistry. The other case gives us clear relative stereochemistry. So throughout this, you'll see me using the same alkenes over and over. It's not that those are the only examples. It's just that they demonstrate the piece of the puzzle that we're interested in seeing. Are we getting regioselective addition, which we'll show in just a moment? And then, as an add-on, do we have relative stereochemistry to worry about, and does it get us anywhere? We could also combine these into a cyclic alkene that's unsymmetrical, but at that point, we're looking at primary versus secondary carbons, secondary versus tertiary carbons. That's not really that massive of a difference. So where we're looking at the top one, we would get really good control primary versus tertiary carbon. Here we're looking at secondary versus tertiary. We'd see more of a mixture. It's not as good of an explanatory alkene. Doesn't mean there won't be a preference, it just won't be as drastic. All right, so those are the basics. Now, let's talk about the examples. So the first example that most textbooks will talk about is one where regiochemistry is the issue, and that is the addition of HX, meaning one of the halo acids. Usually the textbooks will use HBr. So at this point, I generally quiz the class. Why is this going to happen? One of the benefits of an online lecture is we don't have those long awkward pauses while I wait for answers. So it's going to happen because we have a lot of polarization here. The hydrogen is tiny, the bromine is huge. That's not a really good orbital alignment. There's a buildup of charge, and therefore an attraction to loosely held electrons, i.e. the pi bond. Now, that brings us to the next step. Well, attraction doesn't always lead to reaction. You know that from every person you've ever looked at twice on the street. You didn't go home with every one of them, hopefully. But attraction, just something that's attracted, doesn't necessarily mean a reaction is going to happen. There has to be a reason. As it turns out, hydrogens with a positive charge have a very specific reason for letting go of the ion they're attached to, or the atom they're attached to form an ion. It's called being an acid. A Bronsted-Lowry acid or an Arrhenius acid, to use the older definition, a hydrogen donor or proton donor. So that's side one. The other side is there has to be a reason for the alkene to want to do something. Well, that's the point which we talked about much earlier in the course, that our pi bond is weakly held electrons, which means they're electrons that we can break off there and do things with. So that's exactly what happens. Those pi electrons attracted to the HBr, so we see an attack on the hydrogen. Now, it's going to let go of the bromine because it wasn't holding on that well in the first place. It's a strong acid. Then we're going to end up with the bromine ion as our leftover, the bromine anion. And then what? Well, then we have two possibilities. Where did the hydrogen end up? It either ended up on the end, and I'm going to circle it here to make clear which one we're talking about, or it ended up on the inner one. And since the leftover carbon has nothing, it gets a cation. So our question here becomes one of cation stability. Now, we talked about that in class a couple of weeks ago. What makes for a stable cation? And the answer is one of two things. Resonance, not applicable here, or hyperconjugation, which is applicable here. We do have carbons adjacent to the cation with hydrogens attached. In the primary cation case, the lower one I've drawn here, there's only one carbon adjacent to the cation at all, and it has a total of one hydrogen. So this is about as low on the hyperconjugation scale as you can get. There's very little helping to stabilize a cation on a primary carbon. That's the reason they basically don't ever happen. They don't have sufficient stabilization, so they stay home. The tertiary, on the other hand, not well drawn in this case because I avoided drawing all of the hydrogens, but I'll draw them now. Now I have my newly added hydrogen. I also have 8 others on all of the adjacent 3 carbons to the cation. This is winning the lottery in hyperconjugation terms. This is as good as it gets. This is the maximum amount of hyperconjugation that any given cation can have. 9 adjacent hydrogens bound to carbon with accessible electron clouds to help stabilize a cation. When you're given the choice of forming a tertiary cation, it's going to happen. And more to the point is some secondary cations will even rearrange to get to a tertiary one. We're not going to worry about that for this chapter, but the point is a tertiary cation is one of those, energetically favorable things that comes up in a lot of context later. So yes, it's a good case to be in. That's the only thing that's going to get us anywhere. That's the only one that forms. So our primary one is not happening at all. None. Zip, zilch, nada. It is not going to happen. So what's going to happen then is the bromine will attack the cation. And when that happens, we're then going to be looking at a bromine on a more substituted carbon, the hydrogen on the less substituted carbon. So regio-specific. So I'm going to have this, again, I'm only drawing the hydrogen of interest here, and I'm drawing the bromine probably a little bit inaccurately by representing it three-dimensionally. It's not going to have any preference to which side it goes to because a cation is a planar intermediate. But here's where that problem comes in. We have free rotation, so even if we knew which hydrogen was which on that far right carbon, we still wouldn't know what the bromine's relationship was to it because the bond in between those has free rotation. So we can't use this as an example for stereochemistry. We can't tell how it added. Mechanistically, we know there's no control because the cation is planar. But we can't tell because this is a bad example. So generally, if I had to prove the stereochemical, this is what I would want to do. I would take an example and load it up. All right, so we're going to take an example here that's symmetrical but does not have hydrogens on the alkene. That way I can specifically see the relative orientation of the hydrogen versus the bromine as I go forward. So if I add HBr to this, what I get is actually a mixture of two stereoisomers. Sort of. I get a mixture of two relative stereoisomers. What I'm really going to get is a mixture of enantiomers. And that's going to be a problem for us. Not really, we're not going to assign them, but just so you know that that's what happens. I end up afterwards with the cis, try again. The cis stereoisomer drawn this way. I also will have a cis stereoisomer like this, where they both added to the bottom side of what was the alkene. That'll be a pair of enantiomers. Those will actually be there in a 1-to-1 ratio. It's a racemic mixture. It's what resorts from a planar functional group unless you have something that's chiral as one of the reagents, and we don't. We're not going to worry about that. But those are still both relatively syn additions. Both the H and the Br are on the same side. The cation intermediate is actually planar. So what I'm going to get, not only are those two, but these two, where now the bromine and my new hydrogen added to opposite faces. Why? Because we're going through a cation. Every time we go through a cation, our intermediate is flat. A flat intermediate does not have a three-dimensional preference. It's a two-dimensional carbon at that point. There is no definition, top or bottom, period. Now, reality is, I wouldn't draw all four of these. I don't expect you to draw all four of them. You draw the two that represent syn and anti-addition, the ones I have, the lower two, and just write plus its enantiomer. That tells me that you realize we're talking about relative stereochemistry, not absolute. That's acceptable. You would give me an answer there that's complete, that implies you know there are four isomers, but drawing them is redundant because you have no control over R or S at any point in this reaction. So we're not going to bother to talk about it. If you want good practice, go and assign R and S for all four of them. That's good practice for the final, but you don't have to do that right this second. It's not going to be on this exam. It's not part of alkene reaction.